You know that feeling, right? Staring at some dense technical doc, maybe a system diagram that just looks like tangled wires.
Oh yeah, trying to find one specific needle in a massive haystack.
Exactly. It's easy to feel overwhelmed. That's what we want to cut through here. This isn't just another summary. This is the deep dive. We pull out the key stuff, the insights that really matter, just for you.
And it's funny how quickly the details can bury the main ideas.
Yeah.
Our job really is to clear a path through all that noise, help you get the essence without getting bogged down.
Precisely. And today we're diving into embedded C programming, specifically with the Zephyr RTOS.
Our guide for this is the book Andrew Eliasz, Zephyr RTOS, Embedded C Programming.
Now look, we know your technical background might vary. Maybe you're deep in engineering, maybe just curious about the tech in everyday devices.
Doesn't matter. We're aiming for clarity, covering the fundamentals right up to some more advanced patterns. You'll get something valuable, regardless of your starting point.
Because embedded systems, they're everywhere, aren't they? Your fitness tracker, medical devices. Understanding them, especially how something like Zephyr manages it all, is pretty cool.
It really gives you an appreciation for what's going on under the hood.
So our mission today, pretty straightforward. We're dissecting real-time operating systems, RTOS, using Zephyr as our main example.
We'll look at multitasking, how they juggle tasks.
Then how those tasks talk to each other, inter-process communication.
And finally, the device tree and drivers, the link between the software and the actual hardware. Sound good?
Let's dive in.
Okay, so first off, why even use an RTOS like Zephyr? In the old days, simpler systems often used, well, a more linear approach, like the big loop design.
The big loop, right. That's basically check sensors, do calculations, update outputs, repeat.
Over and
Here's-
over. That's the gist of it.
Yeah.
Simple, maybe effective for really basic stuff with predictable timing.
But when things get complex, more features, real-time deadlines.
Yeah, that big loop starts to fall apart. Managing timing becomes a nightmare, like juggling too many balls. You end up needing complex code gymnastics or even more hardware.
Okay, I see where this is going. So the RTOS steps in to manage that complexity. But what is it, fundamentally?
Think of it as a software toolkit. It provides services like scheduling, deciding which piece of code runs when.
And ways for different code pieces to work together.
Exactly. Synchronization, communication, all designed for systems where timing is critical and multiple things need to happen, seemingly at once. These independent pieces of code are usually called tasks, or in Zephyr's case, threads.
Tasks, threads. The book kind of uses them interchangeably. In Zephyr, are they basically the same thing?
Pretty much, yeah. For Zephyr, a thread is the basic unit of work the kernel manages. It's an independent sequence of instructions.
And when Zephyr starts up?
It always starts with at least two threads, the main thread and the idle thread.
Okay, the main thread, what's its job?
It kicks things off after the hardware is ready. First, it sets up the Zephyr kernel itself. Crucial step.
And then?
Then it calls your application's main function. That's your entry point, where your specific code begins. And usually it gets a pretty high priority.
Right. And the idle thread? Sounds like it does nothing.
Ha. Well, it runs when nothing else is ready to run. But it's not just idle, usually.
Yeah.
It's often used for power management, saving battery when the CPU isn't busy.
Smart.
And if it's set up as a cooperative thread, it keeps yielding the CPU, making sure other threads get a chance to run if they become ready. It's always there, running in the background.
A background caretaker makes sense. So, loads of threads potentially ready to go. How does Zephyr pick which one runs?
And schedule.
Right, based on
Priorities. That's the key. Zephyr has two classes. Cooperative threads with negative priorities.
Okay.
And preemptible threads with 0 or positive priorities. And here's the slightly confusing part. Lower number means higher priority.
Ah, okay, so priority 3 beats priority 6.
Exactly. And those cooperative threads, the negative ones, they always run before any preemptible ones.
Yeah.
Highest priority overall.
Got it. So we have these independent threads running based on priority. But they can't just exist in isolation, can they? They need to coordinate, share info.
Precisely. That's where inter-process communication, or IPC, comes in. They need ways to, pass messages, signal each other.
And the book lists a bunch of ways Zephyr does this. Semaphores, message queues, pipes, mailboxes, FIFOs, work queues. Quite the toolbox.
It is. Let's start with semaphores. Think of them like signals or maybe keys.
Keys.
Yeah, like you need a key to access a shared resource. A binary semaphore is like having just one key. It's either available or taken.
And counting semaphores.
They can track multiple keys or permits. A thread has to take the semaphore before using the resource. If none are available, it waits until another thread gives one back.
The book mentioned using them for interrupt handling. That sounded interesting.
Ah, yes, a very common pattern.
Yeah.
Interrupt routines, ISRs need to be super fast.
Right. Don't want to block other important stuff.
So the ISR does the absolute minimum, the time-critical part, and then it signals a counting semaphore. A regular lower priority task is waiting on that semaphore. When the ISR signals it, the task wakes up and does the longer processing work, keeps the ISR short and snappy.
Clever. Okay, what about message queues? Different from just signaling.
Definitely. Message queues are for passing actual data between threads, or even from an ISR to a thread, usually fixed-size chunks of data.
It's like sending a little package.
Exactly. Think of a button press. The ISR detects it, puts a message about the press onto a queue.
And another thread picks it up later to handle it.
Precisely. It's asynchronous.
Oh.
First in, first out, usually. But you need to be careful, especially with ISRs, what happens if the queue is full when the ISR tries to add a message.
Ah, right. Messages could get lost.
Yeah.
Okay, pipes are mentioned briefly, but then mailboxes. How are they different from message queues?
Mailboxes are similar sending and receiving messages, but they offer a bit more flexibility, especially with message size.
Not just fixed-size chunks.
Right. Mailboxes can often handle variable size messages and might let you associate more complex data structures with them, a richer way to pass info.
And FIFOs. Sounds like first in, first out again?
It is, but Zephyr FIFOs have a neat trick. They're designed for data items of any size.
How do they manage that?
They use linked lists internally. A common pattern is one thread allocates some memory, puts data in it, and then puts the pointer to that memory to the FIFO.
Yeah, okay.
The receiving thread gets the pointer, reads the data, and then importantly, it has to free that memory afterwards.
Yeah.
Avoids copying lots of data.
Efficient. Okay, last one in that list. Work queues. They sound different.
They are. Work queues let you defer work to a dedicated background thread, the work queue thread.
Defer work. How?
You submit a work item, which basically points to a function your work handler. The work queue thread picks up that item later and runs your function.
Ah, so it's like queuing up function calls.
Pretty much.
Okay.
Really useful for stuff you shouldn't do in an ISR, like that button press example again. The ISR just queues the work item quickly.
And the work queue thread handles the actual response later at a lower priority.
Exactly. Zephyr even has delayable work, where you can schedule that function to run after a specific delay.
Okay, lots of ways for threads to communicate. The book also talks about synchronization patterns, keeping threads from tripping over each other.
Yeah, essential stuff. You need ways to manage shared resources safely. The book mentions critical sections code blocks that must run atomically without interruption.
To protect shared variables, for instance.
Right. Then there's activity synchronization, one thread waiting for another to signal an event, maybe using event registers or those counting semaphores we discussed.
And resource synchronization, controlling access to hardware.
Yes. For more complex scenarios, maybe managing multiple inputs, there's the daemon task pattern, a dedicated task handling inputs and dispatching work.
You also hear about mutexes and condition variables. How do they fit in?
Mutexes, mutual exclusion locks, are fundamental for protecting shared resources. Think of it like a talking stick.
Only one thread can hold it at a time.
Exactly. A thread locks the mutex, accesses the resource, then unlocks it. If another thread tries to lock it while it's held, it waits. Prevents race condition.
And condition variables.
They often work with mutexes. They let a thread wait efficiently for a specific condition to become true, rather than just constantly checking while holding the mutex.
So lock the mutex, check the condition. If not true, wait on the condition variable.
Right. Then another thread changes the condition and signals the waiting thread. The waiting thread wakes up, relocks the mutex, checks again. Much more efficient.
The book flags deadlock as a potential problem here. Sounds bad.
It is. Deadlock is when two or more threads get stuck, each waiting for a resource the other one holds. Like a gridlock.
The dining philosopher's problem.
The classic example. Everyone grabs one fork and waits for the other, nobody can eat. Dijkstra's solution usually involves enforcing an order for acquiring resources to break that cycle.
Okay. Another pattern mentioned is producer-consumer. Sounds common.
Very common. You have producer threads creating data, putting it in a shared buffer.
And consumer threads taking it out and processing it.
Right. The challenge is coordinating producers don't add to a full buffer, consumers don't take from an empty one. And you need to protect that shared buffer itself, usually with mutexes or similar mechanisms. Zephyr has examples showing this using kernel queues, even considering security with sandboxing.
Lastly, for this section, system calls. What's their role?
System calls are the gateway for user code to ask the kernel for services.
Why the gateway? Can't user code just do things?
Not always, especially with memory protection. User code runs with fewer privileges. If it needs to do something privileged, like talk directly to hardware or manage system resources,
It has to ask the kernel.
exactly, it makes a system call. The kernel takes over, checks the request, does the work safely, and returns the result. It's key for stability and security. The book points to fsyscall.h and .c for examples in Zephyr.
Okay, that makes sense. We've covered how the software tasks run and talk, but how does this software actually, control the hardware? That brings us to device drivers and the device tree.
Right. A core idea in Zephyr is decoupling the driver API, how your application uses a device from the low-level hardware details.
For portability, so you can swap hardware without rewriting everything.
Exactly. Makes code much more reusable. Zephyr's model is influenced by things like the Linux character device driver model.
In this device tree, it's like a map of the hardware.
Precisely. It's a data structure describing the hardware on the board, peripherals, clocks, interrupt connections. It tells the OS and drivers what they're working with at boot time.
How's that different from KCOM? That also configures things.
Good question. Device tree describes the hardware that's present. kconfig configures the software features and drivers you want to include in your build. Hardware map versus software recipe.
Got it. So this device tree map, it must have a specific format.
It does. It's a tree of nodes. Each node represents some hardware. Nodes have properties, key value pairs describing characteristics. Clock speeds, register addresses, which interrupt line it uses. The structure often mirrors the physical hardware layout. It also uses aliases, friendly names for nodes, making code cleaner.
How does a specific driver know which piece of hardware in the device tree it's supposed to control?
The key is the compatible property in the device tree node.
Compatible.
Yeah, it's a string or list of strings identifying the hardware type like VND, device model. Drivers look for nodes with the compatible string they understand. That's how the OS matches drivers to devices.
Okay, the driver finds its device description. How does my application code then, talk to that device?
Zephyr makes this pretty standard. You usually use a macro, device tget, passing it a node identifier from the device tree.
And that gives you?
A pointer to a device structure, a software handle for that hardware. Then, crucially, you check if it's ready using device ready.
Makes sense.
And for common things like GPIOs, there are helper macros like GPIO-tsecbegs. It bundles up the GPIO controller device and the specific pin number for you, straight from the device tree info.
The book uses LEDs as an example. How would that look?
Okay, in the device tree, you define a node for your LED. Give it a label, say, LED to 0.
And properties.
Yeah, properties saying which GPIO pin it's connected to, maybe if it's active, high or low.
Then in the C code,
You'd use GPIO spegit via node label,
Yeah.
RTOS. That macro reads the GPIO's property from the LED node and sets up a structure with everything you need, the GPIO device pointer, the pin number.
and then you can just use the standard GPIO functions to turn it on or off.
Exactly. GPIO pin configure, GPIO pin set.
Uh.
The device tree handles the hardware specifics.
Nice abstraction. The book also highlights the UART driver, especially for debugging.
UART, Universal Asynchronous Receiver Transmitter. Super common for basic serial communication. Just TXD for transmit, RXD for receive, and ground at its simplest.
Need matching baud rates, right? Speed.
And sometimes flow control signals, like RTS, CTS. But for debugging, the key thing is often the virtual COM port over USB on dev boards.
That's how print works, sending messages back to the PC.
Usually, yes. Print often outputs over this virtual UART. Invaluable for seeing what your threads are doing, printing logs. Zephyr also has a more advanced logger module, but print is the quick and dirty way.
What about other common interfaces like SPI and ITC?
Also fundamental. SPI's serial peripheral interface is synchronous, uses a clock line, generally faster, but needs more wires, often including a separate chip select per device.
And ITC.
Integrated circuit. Only 2 wires data, SDA, and clock, SCL. Great for connecting multiple devices with fewer pins, but usually slower than SPI.
And these are also defined in the device tree.
Absolutely. Which bus they're on, I2C addresses, SPI clock speeds using properties like SPIMAX frequency or I2C address, and the CTPOs for configuring SPI chip selects. The compatible property links them to the right driver.
It really feels like the device tree is the central description linking software to hardware. The book mentions macros to access this info in C code too.
Yes, a whole set of DT macros. DT in a DHAS prop checks if a property exists. DTPRP reads basic property values, integers, Boolean strings.
What about interrupts?
Macros like DTNUIUERQS tell you how many interrupts a device has, And DTRQBYDX gets the details for a specific one, the IRQ number, flags. There are also macros like DTP-ANBLT to follow links or fandles between related nodes, essential for writing drivers and hardware-aware code portably.
Okay, switching gears a bit. How do we actually build and work with these Zephyr projects, the development environment and tools?
Like the workflow? Zephyr primarily uses CMake as its build system generator.
CMake, okay. Heard of that.
And there's a command line tool called West. It's written in Python and acts as a kind of meta tool.
What does West do?
It handles fetching Zephyr source code and all its dependencies, updating them, setting things up for CMake, actually building the code for your target board, and flashing the firmware onto the hardware. It streamlines a lot.
The book really seems to like the VS Code integration, especially with the NRF Connect SDK.
It's very good. The NRF Connect extension for VS Code provides a nice graphical interface. You get views for managing project files, easily selecting build targets, exploring the project structure.
Like seeing the device tree visually.
Exactly. There's a device tree view. And actions for building, flashing, debugging right from the editor. It definitely lowers the barrier to entry, makes things feel more integrated.
And what about actual hardware? What boards does the book suggest?
Depends on what you want to do. For Bluetooth Low Energy, BLE, Nordic's NRF52 and NRF91 boards are very popular and well supported.
What if BLE isn't the main focus?
Then boards from Espressif, like the ESP32 series, especially for Wi-Fi, or ST Microelectronics Nucleo boards, are great general-purpose choices with strong Zephyr support. Zephyr is also supporting more advanced multi-core chips now, mixing ARM and RACV sometimes.
Now, one tool that sounded really powerful was Renode, emulating hardware.
Renode is fantastic. It's an open-source emulator that lets you simulate entire embedded systems, CPU, peripherals, sensors, everything in software on your PC.
So you don't even need the physical board to start coding.
Often, no. You can develop, test, debug your firmware before the hardware arrives, or if it's hard to get. It supports various architectures like ARM, RACV, even network simulation.
Does it run the exact same code?
Usually, yes. The same binary you'd flash onto the real board. That makes it amazing for automated testing, CI/CD pipelines. The book differentiates it from simulators, which are often higher level. Renode emulates the hardware behavior closely.
How do you use it?
You load a platform description file defining the virtual hardware, load your compiled firmware, and start the simulation. You can interact via a console, debug, observe. Very powerful.
Okay, let's talk connectivity, crucial for IoT. The book covers Bluetooth Low Energy, BLE, and also general networking, Ethernet, Wi-Fi, TCP/IP. Let's start with BLE.
Right, BLE. The go-to for short-range, low-power wireless. Think wearables, sensors, wireless mice.
Key concepts.
Advertising devices broadcasting their presence, scanning devices listening for ads. Connections for two-way data. Then roles central, like a phone-initiated connections, and peripheral, like a sensor accepting them.
And GATT and ATT, those acronyms pop up a lot.
Yeah, GATT is the generic attribute profile. It defines how data is structured using services and characteristics identified by UUIDs.
Like defining what data a heart rate sensor provides.
Exactly. And ATT, the attribute protocol, is how that data, those attributes, are actually exchanged over the connection using commands, requests, notifications, indications, different ways to read and write data.
And Zephyr, via the NRF Connect SDK, helps build these BLE apps.
Definitely. They provide solid APIs. The book has examples like a basic peripheral advertising itself and a central device connecting to, say, a heart rate monitor and reading data. It covers the whole flow.
Okay, moving beyond BLE to wider networks, Ethernet, Wi-Fi, TCP/IP.
Zephyr has strong support here too, essential for many IoT devices needing internet or LAN access. It has its own network stack.
How do you program networking apps?
You can use Zephyr's native APIs or the standard BSD sockets API, which is familiar if you've done network programming elsewhere. There's also a network management API for configuring interfaces, IPs, etc.
Interfaces have states, right?
Yep, an administrative state,
Right.
on off by the app, and an operational state reflecting the actual link status, including the physical layer.
The book mentions a TCP Echo server example.
Right, a classic example. It often uses a separate thread for each connected client. For Wi-Fi, Zephyr supports connecting to access points, handling security like WPA2, WPA3. The NRF 7002DK board is mentioned as a platform for trying Wi-Fi stuff.
Cool. One last communication mechanism the book introduces. Z-Bus. Sounds Zephyr-specific.
It is. Z-Bus is an application-level message bus within Zephyr. It's based on the observer pattern.
Observer pattern.
Yeah, components can publish messages onto named channels.
Mm-hmm.
Other components can subscribe to those channels and get notified when new messages appear.
So loosely coupled communication. Components don't need direct references to each other.
Exactly. Promotes modularity. Key parts are channels, messages, which carry data, and observers, subscribers, or listeners that react to messages. You publish, read, or subscribe.
What's a use case?
The book suggests maybe a timer interrupt triggers a sensor reading. The reading could be published on a ZBus channel, and other parts of the system subscribed to that channel would then react to the new sensor data.
Wow, okay, we have covered a lot of ground today.
We really have. From the basics of multitasking and how threads talk using IPC,
To the device tree and drivers connecting software to hardware.
then the tools like West and Renode, and finally connectivity with BLE, networking, and ZBus.
It's amazing how these pieces fit together in Zephyr to build complex embedded systems.
Absolutely. And remember, this deep dive gives you the foundation. Each of these areas, IPC patterns, driver development, BLE protocols, they all go much deeper.
So this is really just the starting point for you.
Definitely. We hope you'll dig deeper into whatever caught your interest or fits your projects.
So maybe a final thought to leave you with. As devices get more complex, more connected, how much more critical will these RTOS principles, efficient multitasking resource management, become?
That's a great question. And another one, maybe. With IoT security being so vital, what are the biggest challenges, but also opportunities, in balancing the flexibility of open source like Zephyr with the need for truly robust, secure, embedded software?
Things to ponder as you continue your own exploration. Thanks for joining us on the Deep Dive.